All right, so how you guys doing today? Good. So, you guys excited for the spring break or? Yeah. So perfect. All right. So, uh, we're gonna review what we did on Monday again. So, it's really important. So, let's do a bit more of practical problems over here. So we have to consider concentration and the aqueous solution. Okay? Because once we talk about lots of type of chemical reactions, we have to know the concentration so we can find out how many moles of each reactants will make how much of the product so far. So this is something that is very important. So concentration is simply how much you have of something, how much of something, maybe compound A or molecule A, in how much large space, volume. Okay. So this is literally what it means, how concentrated your solution is based on here. So normally we use the mole, which is Avogadro number, how many you have, and this the unit for volume we use a liter. Okay. So if you look at most of the concentration in chemistry, we use moles per liter. So moles per liter simply means how many moles of something, compound, the molecule you have, and how much of the volume in the solutions. Okay. So this is the common unit for the concentration in chemistry. Sometimes we can just simply put capital M. This is our molarity. Okay. Molarity. So this will indicate the concentration of the aqueous solution in this unit. Okay. So let's try to do some problem here. Okay. So if you have about 10 grams of potassium, okay, and then you try to put this in some container. All right, so you put the 10 grams of potassium hydroxide, 10 grams over here, okay, and then you try to fill this up to maybe 0.5 liter. Okay, so you can say same as 500 milliliter, because the 1,000 milliliter is equal to 1 liter. Okay, so this is what you can do. Okay, so maybe you can say, oh, then what's the concentration? Okay, so we want to use the concentration-wise moles per liter. Okay, so this is what we need to do. So to get the numbers for concentration, the first thing you need to do is, we need to know how many moles we have for 10 grams of potassium hydroxide. Okay, and then maybe we can do the unit volume to make the concentration number then. Okay, so but the problem is we only have a number for the mass, which is in gram. So if you have an actual mass, you can try to divide that actual mass in grams by formula weight or molecular weight. Okay. So what happens to this one if you divide your actual mass by formula weight or molecular weight? That gives the numbers in mole. So in that way, we can find out how many moles you have in per unit volume in the next step. So let's do this in here, which is 10 grams. And then potassium, this is approximately about 39. Okay, this is about 16. This is about 1, right? These are all in your periodic table. So try to copy the number you see on the periodic table, which will be given also exam 2 anyway. So if you do all of that, this should be about 56.1 gram per mole. Okay, so now you got the formula weight there. So simply adding 39 potassium, because we need 1 potassium, 1 oxygen, 1 hydrogen in this potassium hydroxide. So we're just gonna add 39 from the potassium, 16, well 50.99, but oxygen here, and this is 1.008, but just 1. So, but if you just copy all the numbers from the periodic table, you just add them all, you can get the formula weight. So you can actually see those numbers, units cancel out. This will be approximately 0.178, okay? Moles. So now you can say, if you have a 10 grams of potassium hydroxide, that means you're going to have this many moles of the potassium hydroxide will weigh about 10 grams, okay? So now you know how many moles of potassium hydroxide right now by simply doing one-step division calculation. Makes sense, right? Okay, perfect. So whenever you have a moles now, so we have how many moles we have right now? This is done. Okay. The problem is it has to be in each liter. So this is per 1 liter. But your solution volume is about what? 0.5 liter. Okay. So then just you have numbers in the moles divided by numbers in liter. Okay. So if you have just numbers of moles of something, in this case it will be KOH, divided by the volume in liter, that will give you the concentration. Because the concentration itself is just simply what? Moles per liter. So what I'm gonna do is, we got the moles number here, which is 0.178 moles. Okay? And then you're gonna divide this one by 0.500 liter. So because it's just there. Okay. So then you get a moles per liter number, which is this one. So this is what? This is the same as you just multiply this number by 2, because you're dividing this number by 0.5. That is the same as you double this number. Okay. So this will be 653, right? So 0.356 molar. So if you have a 10 grams of potassium hydroxide and put it in the beaker or glassware in a container, and if you try to volume that solution up to 0.5 with water, you add a lot of water until you get the total volume, which is reaches at 0.5 liter. That concentration has to be this one. Okay, so that's the something we can do with the concentration in here. Okay, makes sense, right? Okay, let's do. Okay, so let's try to do another problem together. Okay, so let me try to do. How about we have a sodium sulfate? Okay, and that is let's try to another one. 15 mils of this sodium sulfate solution. Then the concentration is about 0.5 molar. Okay, so now we have another problem here, but we're actually going to do this in the opposite direction here. So if you have a sodium sulfate solution here, which is this much concentrated, and this is how much volume the solution is. Okay, and then we want to find out, how many grams of sodium sulfate should be there in this solution. Okay, this is what we're gonna do now. So basically, we're just gonna do the opposite directional calculation from the one we just did today. So we're gonna start with these two now. Okay, so we start from these two numbers. So this is the same as 0.50 molarity is same as moles per liter, right? Okay, and then if you have a concentration number, remember this one: concentration times volume in liter is the number of moles. Okay? So the problem is here we have numbers in what? Milliliter. Okay, so we have 1,000 milliliter should be equal to 1 liter. Okay, so if you do this one here, 15 milliliter, just do the unit conversion here, right? Okay. Okay, so then you can have the old units cancel, and so this will be 15 divided by 1,000 times by 1. Okay, so that will be 0.015 liters. Okay, makes sense, right? Okay, so now we have numbers in liter for volume. Okay, so we did the unit conversion, so we're happy. So we're just gonna do over here. So in this case, you're actually going to multiply these two. Okay, so you can have a numbers cancel here, and I'm sorry, units cancel over here. So that's how you can get the numbers in moles. Okay, I think that should be 0.0075, right? Yeah, I think so. Yeah. So if that is the case, you have a 0.0075 moles of Na2 and so forth in your solution now. Okay, makes sense, right? Because so forth. And then you have to do is that whenever you have a number in moles, which is this number. Okay, so if you have numbers of moles, okay, times molecular weight or formula weight, which is gram per mole, right? And think about it. This is a number in moles, and if you multiply these two, moles number and the formula weight or molecular weight, you get a moles unit cancel, and you can finally get the numbers in grams. Okay. So once you get this number here in moles, I'm just going to multiply by it's a formula weight here. Okay, so that will be 0.0075 moles times. If you do all that, finding all the sodium 23, sulfur and oxygen and so on, it will be 142.01 something. Okay, and then you'll get the numbers in grams. This is approximately about 1.05, was it? Or something like that, yeah. So, but the key point here is now we just did it the backward. So we just tried to get the numbers of moles of the compounds first, and then we try to multiply that number by formula weight, so you can actually get the numbers in grams. So technically, it means whenever you have this many grams of sodium sulfate and put it in the beaker, okay, and then if you add water until you get to the solution up to 15 mils there, okay. So it's not, so you're not adding 15 mils of water there. If you're adding 15 mils of water, the solution will be slightly over than 15 because of you add already what? 1 grams of sodium sulfate. So it will be slightly less than 15 mils of water you're adding to make the 15 mils of solutions. Makes sense, right? Because of the compound. Okay. So then you have this solution. So this is always going either way. So you're making from here or here. Just use the same method but in the opposite directions. So the key point here is you're able to get the moles number from the concentration times volume, or the grams divided by formula weight. So just the different direction. Okay. Makes sense, right? Okay. So let's do this. Let's do one more together. Okay. Let's do one more. Okay. So you have 120 grams of NaCl, okay, and then you try to put this in the beaker. Okay, so you put this 120 grams of NaCl in the beaker, and then you try to volume that up to 2.7 liter. Okay, so you add water until you get the solution that hits. So here. So what's the concentration? Okay, I'll give you about 3 minutes. And then let's do this together, okay? So you have 120 grams of NaCl. Oh, so this is, once again, you can also find that too, 1 sodium, 1 chlorine. This is about 58.44. Okay, this is a formula weight, so you can use. So if you just use the actual mass divided by formula weight, that will get you the number in moles, right? And then you try to divide that moles of numbers of moles by the total volume of the solution. That's the answer. So yeah, I'll give you about 2 or 3 minutes. Okay, 1 or 2 minutes. Yeah, just the 120 divided by 58.44 and divided by 2.7. Okay, let's do 2 sig figs there because it's 2.7, which is least numbers of the sig figs there. So maybe we can do just 2 sig figs. All right, 30 seconds, we'll do this. Okay, all right, so what's the answer? 0.75, was it? 6, 7? Okay,
Yeah.
good, perfect. So basically, yeah, same, right? So 120 grams, 120 grams divided by 58.44 gram per mole. So cancel, get the moles, which is about 2.05, right? And then once you have this number here, try to divide this number by volume so you can get a concentration, which is moles per liter here, right? So 2.7 liter. So now you have a number in moles per liter, which is same as molarity there. So approximately 0.76. Okay, perfect. Makes sense, right? Okay. Can I move on, right? All right. So the actually, I also talked about the precipitation product percentile. Well, let's hold on to that for a moment. I'll think about it more. I think they might be too hard. So just let me think about it. But other than that, we'll move on to the next part. So on Monday, we also talked about the redox reaction. So redox reaction simply is about the two types of the exchanging of the proton. So the first one is the oxidation. The other one is the reduction. Okay. So these two in total, we call redox reaction. So if something is being oxidized, the other will be reduced because this oxidation simply means loss of electrons, okay? And the reduction simply means gain of electrons. Okay? So this is why it's happening at the same time in the redox reaction. Oxidation, reduction together, we call reduction. So before we get to the actual problems or the example that we can try, let me tell you several rules that I want to remember. Okay? So the first one is if it's something that or the elements, if they're in elemental form, the oxidation number is 0. Okay, so oxidation number is the number we're going to use for finding out if this one is being reduced or oxidized and which part of the redox reaction we're looking at. But for now, I'll explain. Don't worry about it. Just try to remember this one. The first one is the elements are in the elemental form. That always has to be oxidation number 0. Okay, so this is the first one. So the second one is if it's a monoatomic ion form, the oxidation number of that ion is same as the formal charge of the ions. That is the second rule. So if we have maybe sodium cation here, we can say, oh, sodium now is a cation. It has +1 at its oxidation number. Okay, that is the second one. Okay, the third one is a bit tricky, so don't worry about it. I'll also do the practice problem for this one, but you can say non-metal use elements usually, I say usually, not always, usually have negative, negative oxidation number. But there's a few exceptions. Okay, I'm gonna tell you sometime soon today. Don't worry about it. But usually, if you think about the like non-metal part is where you can find in the periodic table on the right side of the periodic table. It's like chlorine, fluorine, oxygen, all become most likely negative oxidation number because it's their non-metal elements. Okay, so that is the case. But there is exceptions. Okay, so it actually tells you. Implied message here is all metal elements will tend to be what? Always positive. Okay? Unless there's very extreme exceptions, they'll become follow these general trends in the oxidation. Okay? The fourth one, if you have sum of oxidation number of elements in the compound should be 0 if the compound is neutral. Okay? So if there's no formal charge, it's a 0 formal charge on the whole compound, the sum of each element's oxidation number should be 0. Okay, that's what it says. Okay, so yeah, just try to try to read the 4 rules like time to time, and you can also use those information when you try to specify the redox or the oxidation in full redox reaction when we do the problem together. So let's try to do some problem here. So the first one, okay, is A2S over here. So in this case, you can assume that this one is the non-metal. You see the surface on the right side. So you can say, oh, this has to be most likely negative in the oxidation number. And the hydrogen here, if you look at the first column at the top, this is hydrogen, which will normally become positive charge, +1 charge in here. So in this two, this combination, this compound, there's 1 plus chargeable cation, there's 2, and 1 sulfur here. So that makes each hydrogen will carry the +1 as a formal charge and also the oxidation number. So oxidation number for hydrogen here is +1, but there is a 2. But as you can see, this is a neutral compound, right? Neutral here. So then this will become +2 in total, because +1 times 2 is +2. To be 0, it has to be -2. So if I ask you for the oxidation number for sulfur in this compound, you should say it's -2 because it's hydrogen. And now it's 0. Makes sense, right? Okay. All right, so if that is the case, okay, so we have all monoatomic elements here. So in this case, there's no variance in the electronegativity whatsoever. So in this case, in the first rule, it's 0, no matter what. Okay, so it is an element form. We don't care because there's nothing else attached to it. It's very monoatomic elementic form. Then no matter what, just 0 oxidation number. Okay, so this is quite easy one. The next one is this one. Okay. Okay, so in this case, you have chlorine here, but it's in the second last column. So it'll be -1, but there is a 2. Okay, so in this case, sulfur will become actually not negative, positive over here. Okay, so we have a -1, but there is a 2. but it has to be sum in 0 because neutral compound. So it has to be +2 because there's only one sulfur here. Okay, so the one sulfur, which is +2 oxidation number. Each chlorine has -1. It's the potential cation charge. I'm sorry, anion charge, but also the oxidation number as well. Okay. And then this is a bit tricky one. Okay. This is a bit tricky. Okay. So in this case, this is metal, but this is in the group 1. So this is +1. There's 2. So +1, +2. Okay. Over there is +2, right? And then this oxygen is the second column in your second last column in your periodic table. So it will be -2. Okay. So oxygen is always -2 in oxidation number. This is always true unless they're in the POC side. In the POC side, they're -1. Okay, but except the POC side 4, oxygen is always -2. It's the second last column here. So this is the here, which is -2, but there are 4. Okay, so there's 4. So that makes what? -8. Okay, so in this case, you have compounds that neutral, but this is the what? -8. You have some positive one is +2. So to make all this 0, the sulfur has to be, there's only one sulfur here, has to be 6. Okay? Kind of makes sense? Okay. So it's, yeah. It's just, we'll take some time. So let's do one more. So here's we have the exception here. Okay. So like I said, the hydrogen is +1, but this is sodium is +1 here, right? But whenever you have a hydrogen that chemical bond to the sodium or the alkali metal here, in this case, this is the case that your hydrogen is become -1. So hydrogen is always, not always, but usually +1. But when it bonds to the metal, like sodium, it can be -1. That's the okay. Sodium hydride. Okay. So this is exception. Okay. So this is kind of so this is what we say. What we say, like in number 3 rule, is usually negative or positive because based on your periodic table, this one has to be plus, but because of the metal, you're kind of forced to be negative. So this is a kind of exceptional case. So let's do one more. So once again, if you look at the chlorate, okay, this is kind of tricky because now you have to have you have a negative charge in this hole. So that means you have a sum of each element oxidation number has to be not 0, but it has to be -1. Like I said, if the compound is neutral, the sum has to be 0, right? But this one is -1. So that means if you added all this chlorine and oxygen number all together, it has to be -1, not 0. Because the formal charge is -1. Right? So neutral is 0, so that's why some of them has to be 0. But this one is a negative charge, so if you add all the oxidation number in each, has to be -1 here. So in that case, the chlorine is non-metal. So like I said, it has to be a negative number in oxidation number. But because of the oxygen, this is an exception for non-metal oxidation number. When it bonds to numbers of the oxygen, oxygen, like I said, always -2, unless they're in the peroxide type of form. So then it will make what? -2 times 3, -6. Okay? And then -6 plus the one chlorine oxidation number has to be -1. So the X should be what? 5. So in this case, your oxidation number of the chlorine, even though it's a non-metal, will become positive. So this is also exception. Kind of makes sense? Kind of makes sense. So obviously on your exam, I don't think I'll put the exceptional case. I'm always going to put the very easy, straightforward oxidation numbering type of problem. So don't worry about too much, but I hope just remember this one for your information. Okay. Make sense, right? Does it make sense? Good. Okay. So let's actually do some the practical problem with this one. So you'll find out why we're doing this for this redox reaction. Why we need to find the oxidation number. Here's the reason why. So this is one. This is a quick review from the Monday. Okay, this is a quick review. So look at this one here. This monoatomic element form is the oxidation number for magnesium is 0 here. This one is a +1, right? And this is negative first column, second last column, +1, -1. So oxidation number is 1 for hydrogen, -1 for the chlorine here. Okay. And then this is chlorine, -1, but there are 2. So it's the -2 in total in this part. So this magnesium now has to be +2 now here to be in sum 0 because it's a neutral compound. And then this is also monoatomic, just hydrogen, so it'll be 0. Okay. So in this case, if you look at this one over here, the magnesium is once 0 in oxidation number become +2. Okay, means this magnesium what? Lost electron. Because when you electron is negatively charged, so if you lose 2 negative electron, they become 2 positive. Because electron is negative. So this is what? Loss of electron, right? From the magnesium view. Okay? So this is what? Loss of electron. This is oxidation. That means, once again, if something is being oxidized, the other one is being reduced right now. Which one is it? It's this one. Okay? So it's this one. So chlorine stays as -1, same. But this one is 1 + 1 by 0. So it's only possible when it gains -1. The +1 to be 0 has to gain -1, right? So that is same as gaining electron, because you're getting something negative, that means you're gaining electron. So that is what? This one. Okay? So this is gain of electron. So this is what? Reduction. So as you can see, they all pair up together. Redox. Okay? Makes sense, right? Okay. All right, let's do one more. What's the? Did you copy it? It's good. Okay. All right. Let's do this one. Okay. So in this case, yeah. So in this case, same thing here. So this is the elemental form. It's just the same elemental form, right? So it'll be 0 here. But this ion form, the sodium is +1, and also iodine is the second last column, is -1. Okay. And then the same here, +1, -1 over here, and this is a 0 because it's same mono elemental form, so it's 0 here. So if you look at this one here, this chlorine was 0, but become -1. Okay, and the iodine once it was -1 become 0. You see this one, right? Okay, so that means you're going to have 2. So let's do this one first. Chlorine goes to electrons. Electrons. So what's this one? Can you guys? It's a reduction or oxidation. So 0 to -1, meaning they need to get something negative. That is
It's reduction.
reduction. Perfect. Great. Reduction. Great. and then the other one have two iodine. They give up the electron, so they lost the electron, so it will be oxidation. Okay, so this is kind of the reason why we wanted to look for each element's oxidation number and how it changed from the left to the right during this reaction. And you can find out, oh, this part went through the reduction, this part went through the oxidation. So we have a redox reaction in here. Okay, I know kind of a lot at the same time. Let's do one more. Okay. Yeah, let's do one more and I'll finish it. I'll definitely talk about this a little bit more, and I wanted to cover more part of the accuracy and concentration like problem more. Okay. But today I'll finish with one more and just that's it. Okay. All right. Almost done. Okay. So you guys remember this one, right? This combination reaction, right? So if you look at this one over here, this will become 0 and 0, elemental form. There's nothing much in here, but in here, this is going to be, so look at the here. So unless, like I said, hydrogen attached to the metal, it tends to be what? +1, right? Okay. And then this is +1, but there's a 3. And also it's neutral, right? Okay. So then makes this hydrogen +1, but there's 3. So there will be, in total in this part, +3 oxidation number here. But some has to be 0. So, but there is only one nitrogen. There has to be -3. Okay? So so here's the thing. So well, this will become, the hydrogen part once is 0, right, elemental form. But in here in the product side, it becomes +1. Okay, and the nitrogen wise is actually once 0, but when it actually done with the combination reaction, it becomes -3 out of the. Okay, so this is a kind of a what? Losing electron become positive, right? So this will become perfect. Okay, and then nitrogen will become reduced. Okay, because now it gains an electron. Okay, so yeah, I'll stop here today. Okay, just